So here we have a diesel cycle, and it says the displaced volume of an internal combustion engine is 5.6 liters. So this is delta V, okay? Or more like V1 minus V2, okay? And the process each cylinder of the engine is modeled under Air Standard Diesel cycle with a cutoff ratio of 2.4. So that is V3 over V2 equals to 2.4. And at the beginning of the compression process, we have 95 kPa and we have 27 degrees Celsius. So P1 is 95 kPa and T1 is 300 Kelvin and has a volume of 6 liters. So V1 is 6 times 10 to the negative 3 meters cubed. And we want to determine the net work, and we want to determine the power developed of the engine in kilowatts and the thermal efficiency if the cycle was executed as 1,500 times per minute. Alright, so first thing, we know that state 1 to 2, that is going to be work in. And then we have 2 to 3, we have Q in, and we have work out. And then 2 to 4, we have work out. And then 4 to 5, we have Q out. Okay, so we can start by saying we want to find our S plus 1 value. From that, we can go to the tables, go to 300, and it's 0.06504. And we know that the cutoff is 5.6, so we can find V2 as well. So we have V1 minus V2 equals to 5.6. So it's 6 minus 5.6 equals to 0.4. That is V2. That's times 10 to the negative 3 meters cubed because that was in liters. Um, so we can also find the mass of the whole entire system. Because it's a closed system, we can find the mass by using the ideal gas law. So we can say that PV equals to MRT. And then this, so it's 95 times 6 times 10 to the negative 3 over 300 Kelvin times 0.287. That would give you 95. And that's going to be giving you 6.62 times 10 to the negative 3 kilograms. And we know it's isentropic. So from our formula sheet, we have this part because we have our volumes. So we say S plus 2 equals to S plus 1 minus R of ln of yeah. So here I'm using the actual volume instead of the specific because they're both just specific times mass and the mass is constant, so they cancel out. So we can say that or 0.6 or 0.06504 minus 0.287 ln of 0.4 over 6. And that equals to 0.84225. And that's in kilojoules per kilogram Kelvin. From this, S plus 2, we can find T2 and we can find U2. Okay. Um, And let's find where it is on the table. So it's between these two values. So we have to interpolate them. I'm not going to be writing the interpolation, but I'll do it. So we have our entropies. So we can put 40, so our temperature 2 would be 843 Kelvin, and our internal energy would be 627.53 kilojoules per kilogram. Okay, and from that we want to find as well um, want to find the pressures and the temperature for all of state 3. So we have right now from our energy balance of state 3 to from 2 to 3, so you have U3 minus U2 times the mass equals to Q in minus the work out, and the work out is boundary work. So we have P times V3 minus V2. And we can calculate V3 from this. So we can say 2.4 times 0 times, let me say V. So 0.2 times 0.4 equals 2.4 times 2. So 0.96 liters, or you can say times 10 to the negative 3 meters cubed. So this, so you have this to be 5.6 times 10 to the negative 3, but we don't have the pressure. So from the pressure, we need to find it by saying that PV equals to MRT. Mass is constant, R is constant, so you can just say PV over T of state 1 equals to PV over T of state 2. We have everything, so we can say that P2 equals to 95 times 6 times 10 to the negative 3 times 843 for the temperature over 300 over 0.4 times 10 to the negative 3. And that would be 4004.25 PA. So writing it down here. Oop. Or we can just move everything to make it in terms of Q in. So plus, and then this is 6.62 times 10 to the negative 3. And we need to find our U3 value. So this is okay. To find our U3 value, we can find our temperature 3 value. So same thing here, but instead of saying state 1, we can say state 3. We know the pressures are equal, and we know V3, so we can say D3 equals to V2 times V3 over V2. That would be 843 and then 0. Which equals to 2023.2 Kelvin. And from that we go into the tables, and here is, so it's between these two values, and then we plug them in. Okay, so we get our U3 value equals to 1701.0184 kilojoules per kilogram, or let's just see 1701. And then we have here 1, this minus 67.53 times. There we have. Oh, my bad. This is 0.56. Then you're gonna have 7.1 plus 2.24. These are rounded, and then the actual value is 9.34 or 388 kilojoules. And that equals a QN. So now we want to find S plus 4. We can find S plus 3. So S plus 3, also interpolation. So from these values, we're going to use 1.64, 175 minus 1.61, 794. And we get an S plus of 1.629 per kilogram. Same thing here, plugging this thing again, but it's going to be a little different. So it's S plus 4 equals to S plus 3 minus R of ln of V4 over V3, which is just V4 over V3 is just 6 over 0.96. So 0.96. And you get a value of 1.103. That would give you 1.103 is between these two values. So interpolating for the U value, you're gonna get 7.91 minus 80.35 over and you get U4 equals to 885.314. And finally, or let's move to, and just add this. And for the Q out, we know that it's going to be from state 1 to state 4. From that, we can say that state 1 was, we can just get it from the 300 table. So it's 214.07. So we can, and that's going to give you Q out equals to 4.44 kilojoules. And analyzing the entire cycle, we know that work net out equals to Q in minus Q out. And that's going to be 9.3488. Minus 4.44, and that's going to be equal to 4.905 kilojoules. Let's work net out. That's the answer to your first part. And you want to find it for, then you're going to multiply that by 1500 over 60 because it was per minute. 4.905 100 divided by 60 equals to 122.63 kilowatts. So that's your answer for part 2. And for your last part, it's just work net out over Q in. So that's going to be 4.905 over 9.3488. And we can just do that by, or 9, divided by that. And you're going to get 52.4%. That's your final answer.